transparent oligotrophic waters of Lake Ouiachiquimi were formerly known in French as Lac à l'eau claire, and in English as Clearwater Lake. These waters occupy a pair of meteoritic impact craters, believed to be caused by a first impact some 450 million years ago, and a second adjacent impact around 285 million years ago. The unusual form and origins of this large water body highlight the diversity of lake basin shapes and their diverse geological origins throughout the world. The global land surface is covered by an estimated 21 million lakes, with a total storage volume of about 183,000 cubic kilometers. Lakes are ubiquitous in formerly glaciated regions where countless depressions were created that filled with water, especially in the subarctic and temperate regions of the Northern Hemisphere. In contrast, particularly large and old lakes can be found inside tectonic rifts, such as Lake Baikal in Russia and the African Rift Lakes. About 2/3 of the total volume of freshwater lakes are contained in only the 4 largest lakes: Lakes Baikal, Tanganyika, Superior, and Malawi. Most lakes are much smaller, however, and relatively shallow, often less than 10 meters in depth. Saltwater lakes occur on all continents, and by far the largest of these is the Caspian Sea, which accounts for 41% of global lake volume. The distribution of lake size follows Pareto functions, whereby the most abundant lakes in the world have small areas and small volumes. The morphometry, basin shape of a lake has profound effects on its physical, chemical, and biological properties. Morphometry can be summarized by an area depth curve, called the hypsographic curve, or by a volume depth plot. Lake morphometry and the geological substrates of the drainage basin influence sediment-water interactions and lake productivity, especially that of the extremely productive littoral communities. The greater productivity of small, shallow lakes is usually correlated with the higher water-sediment interface area per unit volume, as found in lakes with lower mean depth. Natural lakes are formed either by relatively fast, catastrophic geological events, or by more gradual processes, and they can be grouped into several main types of origin. Glacial lakes are formed by the erosional and depositional activity of glaciers and represent the highest abundant of lakes globally. Well-known glacial basins include the Laurentian Great Lakes of North America, which date back to the period of ice sheet retreat about 11,000 years ago. Another well-known glacially formed basin is Lake Geneva, where the science of limnology was founded by François-Alphonse Forel in the 19th century. Glacial scouring can also produce smaller lakes, such as tarns and suck lakes, and a string of connected basins called paternoster lakes. Lakes are also formed through damming by morainal deposits and as depressions created by ice blocks in the outwash of morainal debris. These stranded ice blocks then melt out to produce kettle lakes. In permafrost landscapes, thermokarst lakes and ponds result from the thawing and collapse of ice-rich soils. This thermal erosion process is taking place at accelerated rates with ongoing climate warming on continuous as well as on discontinuous permafrost. Permafrost thawing and erosion can also result in large thermokarst lakes, such as here in northeastern Siberia. Tectonic lakes are depressions formed by displacements of the Earth's crust, creating many of the deepest lakes of the world. For example, the Lake Tahoe Basin was formed by block faulting, creating a trough-shaped graben lake with steep sides and large average depth. The most notable example among tectonic lakes is Lake Baikal, which occupies a deep rift in the southern part of eastern Siberia. With an age of 25 million years, Lake Baikal is the world's oldest and deepest lake. It has a maximum depth of 1,642 meters, underlain by 7 kilometers of sediments. This deep basin contains around 20% of the world's fresh water. Another well-known example of a lake of tectonic origin is Lake Biwa, the largest lake in Japan, and drinking water supply for 14 million people, including the cities of Kyoto and Osaka. The lake basin began to form some 4 million years ago and shifted to its current position about 400,000 years ago. Deep drilling has shown that its north basin is underlain by 800 meters of lake and river sediments. And like other tectonic lakes with their long histories of plant and animal and microbial evolution, Lake Biwa contains many endemic species, including the giant catfish, Silurus biwaensis. Volcanic lakes form in volcanic cones or in depressions resulting from the collapse of partially emptied magmatic chambers within a volcano. Maars are a subset of lakes in this category and are volcanic craters that are formed by phreatomagmatic explosions. These are explosions that occur when magma comes into contact with groundwater, and the resultant crater then fills with water to form a lake. Landslides can dam stream valleys and thereby create temporary or permanent lakes. And river activity in the form of erosional and depositional processes can isolate depressions that fill with water and turn into lakes. For example, plunge pool lakes, oxbow lakes, and deltaic lakes. Coastal lakes often form along irregularities in the shoreline of the sea, where currents deposit sediments in bars or spits. These can eventually isolate a fresh or brackish water lake. Karst lakes are formed from the dissolution of rocks such as limestone and dolomite, and they include outcropping lakes as well as sinks termed dolines. Striking examples of karst waters are found in the Plitvice Lakes National Park in Croatia. Wind erosion can form shallow depressions that contain water temporarily or seasonally or longer. These include Aeolian lakes, dune lakes, and playa lakes. Lakes formed in the depression caused by the impact of a meteorite include Pingualuc, a crater lake in northern Quebec that the Inuit refer to as the Crystal Eye of Nunavik. Natural lakes can also have organic origins, such as lakes created by the damming action of plant growth or animal activity, for example, dam building by beavers. For millennia, humans have created artificial lakes by damming streams. The pace and scale of damming, however, increased dramatically in the mid-20th century. Reservoirs, impoundments created by humans through the damming of river valleys, often show a transition from well-mixed conditions upstream to a downstream lake-like regime of stratified waters. Reservoirs provide numerous ecosystem services, including domestic water supplies, irrigation sources, flood control, hydroelectricity, transport routes, fisheries, and recreation. However, the dams also act as ecological barriers, and they fragment the connected network of naturally free-flowing rivers. The retention of fluvial sediments in reservoirs can have far-reaching consequences on downstream river morphology. All lakes are temporary features of the landscape. After lake formation, succession processes start to fill the lake with influxes of river sediments and accumulation of organic matter that is produced within the lake. The succession process may be accompanied by different stages of nutrient loading: oligotrophic, mesotrophic, eutrophic, and hypereutrophic. This process can be greatly accelerated by nutrient pollution and landscape changes caused by human activities. Satellite remote sensing, combined with GIS analysis, is now allowing the mapping of inland waters at multiple scales of resolution, from local to regional and global. In developing the database HydroSheds, the aim has been to produce open-access geospatial datasets that can be then used in regional, global, or multi-scale applications. As illustrated by this digital elevation model and river network for Iceland. The resultant global estimates show that there may be more than 24 million kilometers of interconnected rivers draining the Earth's land surface. River density is highest in wet tropical climates, including the Amazon and Congo basins, as well as in colder landscapes in the north. Rivers account for only an extremely small amount of all freshwater stocks on Earth, but they are major transporters of dissolved and particulate matter from land to sea. River flow, or discharge, is directly related to climate, precipitation, temperature, the drainage basin, area and soils, and effects of vegetation, evapotranspiration. Stream and river channels move laterally within the floodplain because of erosion and redeposition of sediments. The forms of a river channel include 4 general classes: straight, meandering, anastomosing, and braided. And many patterns of channel networks are observed. These patterns depend on geological structure, rock type, the presence of faults, landform shapes, and exposure to climate and vegetation. Several methods have been developed to classify the tributaries of a river and to order them in the channel network of a river basin. In the most widely used Strahler method, the smallest permanent stream is designated as the first order. The confluence of 2 first-order streams creates a second order. The order then sequentially increases by 1 when 2 tributaries of equal order meet. The Amazon River is estimated to be 12th order, the highest order of all rivers. Besides the anthropogenic effects of reservoir construction, climate change is expected to both create new lakes, for example, through permafrost thawing, and to remove lakes, for example, through desiccation caused by drier or hotter climates. These alterations lead to complex changes in global water availability and stream flow. Overall, there has been a global net increase in permanent surface waters between 1984 and 2019, with dams and reservoir filling being the main cause. However, severe depletion of surface waters is occurring in some regions, for example, in the Middle East and the Southwest United States. Large hydrological changes are taking place at high northern latitudes, where air temperatures are rising at 3 to 4 times the rate of average global warming, and precipitation is shifting from snow to rain.